Dear students, hope you all are doing well. Welcome to another very exciting session of the course Mechanical Characterization and Modeling of Tissues. So we had been discussing about the different soft tissue simulants. We talked about quite a few exciting soft tissue simulants like the skin and the brain. So we are going to continue on that and learn about a few more soft tissue simulants which have been developed to date, as well as discuss quite a few really good applications, right? So let's get started. Okay, so the next soft tissue simulant is for the calcaneal fat pad. Calcaneal fat pad is a natural soft tissue which is there at the bottom of your heel, of the heel of your foot. So calcaneal fat pad is something which acts as a cushion while you're walking, running, and doing all daily activities. So it undergoes a lot of cyclic and fatigue kind of loading cycles like throughout your lifetime. So if this is overstressed, at a certain point the calcaneal fat pad can get damaged, right? So the motivation here was for the problem of plantar fasciitis. Plantar fasciitis is a very common term used for heel pain basically, and it also encompasses other sorts of foot pain which are on the plantar or the bottom region of the foot, such as the arch pain or the pain due to pain on the toes due to uneven distribution of pressures and whatnot. But a calcaneal fat pad here is a soft tissue which is of high importance. So in plantar fasciitis, if this calcaneal fat pad gets damaged, the pain can intensify, and sometimes the incidences of plantar fasciitis is due to the calcaneal fat pad damage, right? So with that motivation, we also wanted to look at what is a normal calcaneal fat condition, what is the condition of the fat pad for people or patients with plantar heel pain, also in people with diabetes, right? So diabetes has a very common implication of affecting the foot due to something which is known as neuropathy, where there is no nerve sensation or no sensation at the bottom of the foot, and the material of the foot also changes, right? So these three normal condition, plantar heel pain condition, as well as the diabetic condition, this is where the calcaneal fat pad properties have a clear role to play, right? Like in terms of how well they are done, right? So we wanted to create some soft tissue simulants for the calcaneal fat pad. Of course, we cannot take this fat pad out of a cadaver or a human body that easily. So we wanted to basically create some simulants, and one purpose was to study the calcaneal fat pad properties in normal and diseased conditions like in with plantar heel pain and diabetes, as well as these sometimes we can develop a product which is known as a fat pad cushion in cases where the fat pad is damaged, and that can be worn just like an insole, or can form the part of a heel cup in an insole and provide the right cushioning which is missing due to the damaging of the fat pad, right? So these were the two different motivations. One is the study of the biomechanics and the properties, second is for product development, right? So with this motivation we started developing and the calcaneal fat pad simulant. So here the fabrication methodology was very similar to the other soft simulants. We looked at 4-part silicon, which has worked pretty well for us for the most soft tissue mimicking, because it provides a range of very soft properties to very high stiffness properties, and also has a very clearly elastic and kind of a hyper elastic response with a highly nonlinear touch, right? So the 4-part silicon mixture was again with the two different sets of silicon, one with the shore hardness of 10, A in the shore hardness A scale. Typically this shore hardness value is measured using a durometer. Durometer is a measurement device which you place, it has a small indenter and you can place it on any of the soft materials to measure a shore hardness, right? 30A is a little higher on the shore hardness, right? They were all mixed in different ratios, right? That gave us a bunch of specimens. This time we did not test it under tensile loads, but we tested it under compression loads, because that's what the heel pad is going to get subjected to while you walk or run or stand. So the heel pad dimensions were selected. The heel pad simulant dimensions were basically selected based on uh, review of actual studies where the real heel pad was extracted from a cadaver and tested, right? And also the properties were extracted from that literature to compare with our results. So a diameter of 60 millimeter was selected, and a depth of closely 18 millimeters was selected for this, right? The tests were conducted at two different strain rates, going from 0.8 meters millimeters per second, meters is very high, and 1.9 millimeters per second, fairly low, right? Then the heel pads were also subjected to cyclic strain rates, right? Like where you have loading and unloading of the loads, right? So this was conducted at a 1.96 millimeter per second, so it's a very slowly loading and unloading. Then very high strain rates were also applied in the order of 180 to 1800 millimeters per second. So 1800 is almost millimeters, is almost like a 1.8 meter per second. That's a lot, right? So these kind of very high strain rates were also applied. Why were this specific numbers selected? Because the strain rates had to be the same with what has been done in literature for testing, and that is the only way we can compare apple to apple the stress strain plots or the load deformation plots, right? So that was the purpose. So the tissues we had simulated using the different soft tissue simulants developed were the healthy fat pad, the diseased fat pad under diabetes, and the diseased fat pad under plantar fasciitis, right? So on the figure on the top, you can see a very quick schematic of where the calcaneal fat pad is, and some of the samples which we have developed, which are round samples with a certain depth, right? Then they were placed within a UTM again, and that was under compression load, so we had to do a few things extra to create the right setup, so that there are two flat ends under which the compression happens, and that's where the calcaneal fat pad simulant is sandwiched in between, right? So mechanical tests were conducted in all the declared strain rates, and what we found out as a final set of results and the comparison with the literature is all captured in the plot on the bottom right. So you are looking at the healthy control, which is a very thick dark line. This is derived from the Tong et al. Tong et al. Is one of the research groups with Dr. Tong as one of the key principal investigators, where they have looked at healthy control. Healthy control is same as healthy calcaneal fat pads. They have extracted it from cadavers and they have tested it across these strain rates, right, under compression. The second is plantar heel pain. This is the medium thickness black line, and this is also done as a part of the research by Tong et al. The third one is diabetes. So third one is diabetes, which is also performed by Tong et al.'s research group, which is the thin black line. All these three lines you're looking at are with error bars, right? Error bars basically means these were out of the many tests or mechanical tests which were conducted, the results kind of were distributed across a certain range, right? So that's the error bar when you took out several different samples from different cadavers, right? And then this is followed by all the colored lines which represent all the different compositions which we have developed to simulate the calcaneal fat pad, and we had developed this with the intention of just going from a softer hardness material to a higher stiffer hardness material, and this was done iteratively. We increased the composition and the hardness, and finally the different plots which we had derived from the literature were compared with our compositions, and the compositions which were very close to the literature within the error bars were considered as simulants, which describes either the healthy control, the plantar heel pain condition, or the diabetic condition of the calcaneal fat pad, right? So this is how a quasi-static normal UTM test was conducted, right? And this work is again published as a part of our research in the journal Biomimetics. You're welcome to look at it. The details of the publication are as at the very bottom, right? Okay, so this calcaneal fat pad simulants which we had developed were also subjected to cyclic and very high strain test based loadings. So the figure on the left, you are looking at the cyclic loading where you have the healthy control. This is from another research which is done by Fontanella et al. This is the research group. In the loading and unloading phase, they have taken quite a few measurements. So these people did, like research on the cyclic uh, kinds of loading, right? So we had developed this one control composition to mimic the specific force displacement response, and this was the surrogate with the configuration 60 20 10 10. This basically represents the different ratios by weight of the two mixture amounts of the two different sets of silicon, right? So under loading and unloading, whenever you conduct a cyclic loading kind of a condition, there is typically the plot kind of has a little bit of extra curve to it, and there is the area which you can highlight between the loading cycle and the unloading cycle, right? This is typically the energy absorption or the of the system, right? Like due to the cyclic loading and unloading. Similar observations were seen like for our surrogate, and it compared fairly well. So you are looking at the dark gray or blackish lines for the literature values, and you're looking at the colored lines for the loading. Red one is for loading, and green one is for unloading, right? So most of the results were within the error bars that indicated that our simulant was fairly good to simulate the cyclic conditions. The next one was we wanted to conduct the tests with the surrogate 60 20 10 10 only, because we define this as a control surrogate which we want to test it across different strain rates, repeatability, reproducibility, cyclic loading. So we have to always pinpoint one surrogate composition which we are going to test extensively, right? Rest of them are for just finding where the surrogate composition should lie. So first of all, we hit and trial find the necessary that the surrogate composition should be from 30% of A to 35% of A, let's say 32% of B to 32.5% of B, these kind of compositions which we have for the four parts. And after once we have pinpointed this, we figure out a healthy or a control specimen, and which we compare it across different tests, right? So we did the same. Here we derived some of the literature values where Gregorius is another researcher, Gregorius et al. Their group had basically studied calcaneal fat pad from the real cadavers at the different strain rates of 1.96, 180, and 1800 millimeters per second, right? So we also subjected our same control surrogate to these three different strain rates, and we found some results which were fairly comparable, as you can see in the plots, right? So the black dark line is for the 1.96 millimeters per second strain rate, and the green one, our surrogate composition or the simulant composition was almost very close, almost like an overlap, right? Similar with the dashed lines at a 180 millimeters per second, and also the blue line was able to capture it. When you went for 1800 millimeters per second, the dotted line, which is the value from the literature, was not very far, right? So two things to note here is, first is I had explained this quite a bit like in the previous classes, that whenever you increase the strain rate, the rate at which you are applying the loading, the rate at which you are applying the displacements, the property of the material or the response of the material, be it a soft material or a tissue, completely changes. It becomes much more stiff. So that is exactly what we're seeing here. When we increase the strain rate from 1.96 to 1800, it has drastically increased, right? So is that increase also observed in simulants such as isotropic simulants like built with silicon? Yes, we are seeing that. That is number two. But we are seeing some differences in the response because in the actual tissue you have fibers, so it behaves a little differently when it is subjected to very high strain rates. Whereas in the silicon based simulant you do not have fibers, so there would be some difference between the actual specimen response and the simulant response, And that is exactly what we saw right here. So next tissue simulant which we developed was for a little bit of different purpose. This is known as an artificial heel surrogate. This is kind of an adaptation from the calcaneal heel pad. So we took the properties of the calcaneal heel pad, but we wanted to create the structure of the human heel, right? And what was the purpose here? The purpose here was not to just do a compression test, which we have already done for the calcaneal heel pad, but to do some friction test. We wanted to look at barefoot slips and fall conditions, right? So if you are walking barefoot on a particular flooring and there is a water spill or an oil spill, do you have a high chance of slipping? That is what we wanted to basically measure, right? So we developed a very novel human heel surrogate or a artificial heel surrogate. This has been filed for patent again. So the way this was done was we actually scanned the foot of a person, and based on that we did some post processing with the scan, and we could create extract the shape of the heel, which is usually of concern and which is a part of the slipping condition. So when you actually slip, you are basically you slip at a heel strike typically. So once you have your heel is struck like on the ground, all of a sudden there is lack of friction between the ground and the heel, and due to the contaminant, which is water or oil in this case, it's even worse, and then you have a slipping or lack of friction, right? So that's a similar we wanted to pinpoint what region of the foot is of concern, and that is exactly what we extracted, and we created a negative mold of that using 3D printing, which you can see on the figure on the top left, right? And then we have to build a connector. This is for the purpose of connecting it with a slip testing device. These are typically devices, it's known as a British pendulum tester. This is commonly used in the airports, right? Airports for testing whether the ground is safe for the flight wheels to land. Is it giving enough traction for the wheels? So in a rainy day, and the traction may go down, right? So these slip testing devices are commonly used across the industry. We wanted to modify that device to incorporate this human heel simulant and run some tests on the same, right? So we created this uh, top right, you can see two this human heel simulants, which not only mimics the properties of the calcaneal heel pad, but also the structure of the human heel, right? And we then connected them with the connector, right? The connector was built separately and was assembled, and finally the system was all assembled into the British pendulum tester. So this allowed us to test the heel surrogate in various slips and fall conditions. So the beauty of this is now with this slip design, like slip testing design, we can take this entire portable slip testing device to any flooring, be it in a kitchen flooring or a like hospital flooring, be it in any other places like where there is a possible, or a bathroom flooring where you have a barefoot condition, or flooring of a bathtub for example, or flooring of a swimming pool. So these were all the possible locations where we can place this device and quickly take a measurement, because we already have the biofidelic or the heel model which simulates the actual human heel and also its properties. So all we need is the flooring and the liquid, which is in case of a swimming pool or bathroom it's water, in bathroom it could be shampoo solution or soap solution, so things like that. So we could test it, run a battery of tests like 200-300 tests to find out different results and declare which floorings are safe, which floorings are not, for let's say the bathroom or the swimming pool and things like that. So this was part of a pilot study and ongoing research in the areas of slips and falls, but here also we have beautifully used an artificial human heel surrogate to understand the mechanical properties, right? The next one is an artificial anisotropic tissue. So, so far what we have been talking about is an artificial isotropic tissue. Isotropic means it's a single material, whether you pull the specimen from this side or that side or from the top to bottom, it's going to behave the same, right? Because it's a single material. Now we wanted to create a little bit closer version to what a soft tissue should look like. So we introduced artificial anisotropic tissues, and we created some very crude fundamental versions of these tissue mimics, right? So the way we did this was we selected two different silicon materials, right? And one was a softer material and one was the harder material, the 10A and 30A. And we had basically considered that the we'll create fibers with the harder material, and we will have these fibers embedded within the softer matrix to give it the same definition of how we define any soft tissue macroscopically, right? We define it as a soft composite, right, like which is fibers within a softer matrix, right? So to kind of have that definition designed, we wanted to build this anisotropic soft tissue simulant. We took some specimens and we tested the materials by themselves, and then created the different embodiments like of the different fibers or the fiber locations or the fiber volume fractions which are embedded within the softer material. So these are the four different types of tests which we conducted. Uh, so when we increase the fiber volume fraction, what is this fiber volume fraction? So fiber volume fraction is how much amount of the total volume of the sample is filled with fibers, right? So that's a very clear definition. So if we have a very low fiber volume fraction of 0.17, which you see on the figure on the very top left, the first figure, uh, that means the fiber is either narrow or you have a very small population of fibers, right? So here we just worked with some bulk fibers to just understand the fundamental concepts of what happens when you have a hard material within a soft material, specifically to simulate skin, right? So we changed the fiber volume fraction as intuitive. We found the results to change. The stiffness increased drastically when the amount of fibers or the amount of harder material within the softer material was increased, right? Which we can see very clearly in the top left figure. Then the next is when we increase the fiber spacing. So if you have a lot of fibers, same size fibers, same thickness fibers going across the length, and we increase the fiber spacing, that means we can accommodate a very few fibers. So due to large spaces, the overall property of the sample is going to get much more compliant or less stiff. So the property is going to go down, right? That's the next set of tests which we did. The third set of tests was increasing the number of fibers, right? If you want to club in a lot of fibers within the same space and all the fibers are equally width, right, equal width, so then when we have a lot of fibers directed towards the longitudinal axis of the test, of course the property will go up, it stiffens up, right? And the fourth one is when we change the angle of the fibers. So fibers directed towards the direction of test, which is longitudinal versus orthogonal, 90-degree to that, and all the angles in between. We wanted to see the effect, and it's very intuitive. Like when the fibers are straightforward towards the direction of loading, it's going to behave much more stiffer, right? And that's what we saw in the results. So we just wanted to lay down this fundamental understandings again with the soft tissue simulants to just develop the foundation, right? This is also published as a part of our research in applied bionics and biomechanics. This is a detail of the paper. You're welcome to look at it, right? Okay, then we as we evolved, we have been able to create advanced artificial anisotropic tissues, where if you look at most of the artificial tissues in the slide here, you're looking at majorly very crude kind of setups, like where some fibers are cut in a way like they're cut with scissors or things like that, and they've just put to get a fundamental understanding. Now if you look at the fibers on the top four specimens, you can see very clearly, so one set of fiber is going at a 0 degree, then at a certain degree the angle keeps on increasing, and it's a very smooth kind of setup, right? But this has been made using additive manufacturing, where all the dark lines are representing fibers of a different property, okay, and the rest of it, like which is a little whitish or lighter in color, depicts the matrix. So this is a two material system with fibers embedded in the matrix, but looks much more smoother and nicer, right? Then we have used this anisotropic tissue simulants, which are highly advanced. This is also published quite well. We have used them to study the mechanics of skin grafts, which I'm going to just showcase as very quick snapshot of what skin grafting is. But skin grafts are where you have incisions or slits or holes within the soft tissue, and you want to create a large amount of expansion. So this is using biaxial testing. We are looking at the skin graft property, or trying to create a skin graft simulant. The purpose here is to understand the skin graft expansion, basically, not to have something which is replacing a graft or transplanting, not for that purpose. This is for biomechanical, purely biomechanical study, right? So these are some advanced artificial anisotropic tissues which we can come up after a lot of research, right? So let's look at some of the applications, very notable applications in the area of surgery, which can be beneficial using the soft tissue simulants. So the first set of like examples are to understand soft tissue damage and repair. So one of the motivation here was, we get all different sorts of wounds due to cuts or some form of injury, but have we ever analyzed the wounds? Why do we need to analyze the wounds? Because every wound needs a very different attention. If you have a small scratch, it will heal by itself. But if you have a wound which is really a deep cut which needs some form of stitching or surgical intervention, then there needs to be a standard practice that if the wound is of this much size, this much width, then this much amount of suturing or this much amount of suture force should be placed. These kind of standards do not exist. So most majority of the suturing which goes on up to date is all based on a surgeon's experience. If you go to a new person who has been in the who has been practicing for a year or two, they will basically stitch it in a very different way versus a doctor or surgeon who had been doing this for last 20 years, right? So why do we want to standardize practices? This is very important because this way we can speak a common language, and even the new medical practitioners or doctors across borders, they can have now a common practice or a guideline, at least, that if a wound is of a certain size, this much length, this kind of suturing practices are much more beneficial. That will eventually only help the patients because the wounds will heal much more quickly. This is number one. Second is, if we have these kind of standardized practices, we can feed this information to a robot, which is going to perform a lot of robotic surgeries in the upcoming years, right? So with these two primary motivations, we wanted to study that what are some of the different wound shapes which we commonly encounter in literature, or which many of us commonly get, and how all the deep wound shape and how they can be sutured, and how this overall affects the mechanical property of the tissue when during the wound and after it is being sutured, right? So we did a very thorough biomechanical study to understand all these properties, and this could only be achieved through the development of a soft tissue simulant, which in this case is a skin simulant, right? So we created artificial human skin simulants, and we generated different wound geometries, long and short. Also the wounds were located across top, bottom, and center. These wound shapes were all derived from literature, and based on that we had run some solutions, right? We had placed on these wounds interrupted sutures. This is a type of suturing technique where you have one suture, you end that suture, you place another suture, then you place the third suture, right? And another technique, a very common technique, is the continuous suture, where you keep on suturing. You take the thread and you keep on suturing here, 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 here. Why did we choose interrupted suture? Because this is commonly observed or commonly practiced almost as much as a continuous suture. But another reason was, we were not experts in suturing, so at that time we thought interrupted suture is something which we can place in a better way, right? To be as close as to a real soft tissue suturing or a skin suturing condition as possible, right? We wanted to be as close as possible to the real scenario, otherwise the study is of no use. So we also defined something which is known as a hyperelastic relationship. I'm going to have a session dedicated to hyperelastic models, what they are. So let us skip this for now, the hyperelastic mathematical equation component, but let us focus on the blue region. So the first one is known as a tissue phantom, or an artificial skin, or a skin simulant, right? This is what we developed first. This was followed by a tissue phantom with the wound, right? So we had now created the wounds, and the third one This is just a representative of all the samples which we had tested, right? The third one is a tissue phantom with suture. So now we have placed the suture, and what we are seeing on the right side is all the microscopic images of all the different wound types, right? So we have clearly demarcated the lengths, and we have noted down the different measurements of the wound, and based on that we have classified them as either a long wound or a short wound and a top, center, bottom kind of wound, right? So with this nice set of experimental samples, we started testing, and we found some very interesting results, right? So in the plot on the very left, what we saw was the average stress versus strain for an unwounded and wounded specimen. So we took the average of all the responses, mechanical responses, which we got from testing of all the wounded and the unwounded specimen. Unwounded is the skin simulant by itself, right? And all the wounds are different shapes of wounds. We took the overall properties and kind of took an average of that with the error bars. So when we compared them, we could see a very clear demarcation between the wounded samples as well as the unwounded samples. So we can very clearly see the wounded samples had a property much lower, right? Even the error bars are coming lower, which is fairly intuitive. If a skin is wounded, the property, mechanical property, will degrade. So it was quite intuitive and straightforward. If the results would have been otherwise, then it would have been a concern for our research technique or the methods which we are using, but this was okay. The next one is the figure on the right, where we compared not only the unwounded phantom but also the wounded phantom and the sutured phantoms, like the average values of that. So very interesting result if you see here. While the wounded ones had properties much lower than the unwounded ones or the natural simulant ones, once you have sutured them, right? So the sutured one is the dark line. You're looking at a property much higher than the original simulant. So that means with suturing, the overall material property of the skin becomes much more stiff than its natural version, which is also intuitive because you are placing a suture material which is much more harder than the actual tissue, right? But this was a very clear finding which we got, and we could clearly say that our research results or the methods are accurate, right? So we saw all the sutured specimens showing much more higher stiffness. Okay, the next thing is, so far what we have done in this research is we have only looked at the UTM best overall deformation, load versus deformation. What you do not see here is what is happening within the tissue. So irrespective of how the wound is, whether it's a circular hole or it's a square hole or whatever is going on, all you are getting is an overall response. So sometimes if you do not know what the wound size is or the shape is, you cannot predict back from a response that what could be the possible wound shape or size, right? So it cannot be backtracked. So we wanted to look a little bit closer into the wound, that what is happening with the different wound shapes. The overall response is all great, overall properties we understand. What is happening at a local level? This is known as local soft tissue mechanics, right? So let me just give you a very brief introduction into the local soft tissue mechanics, and I'm then going to talk about this technique, which is a very unique technique, at length in one of the upcoming sessions, right? This is known as local damage study using digital image correlation. This is an imaging technique known as DIC quite commonly. So in this technique, what happens is you try to track the local strains which are developing during a test, right, during an experimental test. The way we did this was, you make different artificial human skin compositions, like that is a standard tissue simulant specimen. Then you create the wounds specifically in all the samples, that is also there. So all the wounded specimens we are taking or considering. Then the next thing is, we put a spray paint. We have to have select a spray paint which is of a unique color or a distinct color. So here we have chosen a spray paint which is white in color. So this spray paint has to be handled very carefully. If you spray the specimen from a very close purview, it is going to create not a spray but a complete layer. If you spray it from a long distance, it is not, there will be a lot of gaps between the spray particles. You want to select a very optimal distance through research, so that you spray all these specimens in a way that the particles are very close to each other, but of different shapes, of course, because you don't have control of how the spray particles are throwing on the surface, right? All these spray particles are a very unique thing, right? So during a test, along with the spray particles, what you do is you capture a video, you capture a high definition video, and you put this video into a post processing DIC software. What the DIC software does is it breaks down the video into multiple frames and figures out that a particular particle, let's say particle number 1 of the spray, how has this moved over time? For a 50 seconds test, has it moved 1 millimeter or 2.5 millimeter on the x, y and z, all the three directions? How has it moved? Here we are specifically looking at x and y, assuming the from a planar standpoint. There is 3D DIC also, but this is, we are talking about a 2D DIC. So let us assume y is the direction of loading and x is the orthogonal direction. So along the x and y, how each particle has moved. These particles are sometimes known as, in a zoomed version, speckles, irregular speckles. So they are irregular speckles because all of them look very different, right? So the speckle patterns are tracked through the entire test, and that gives the overall strain field. How each particle, so think about thousands of particles which are on this particular specimen, they have all moved by a certain displacement. All this trajectory of the displacements are all tracked by the post processing software once you upload the video and cut it into different frames, right? And that will give you the strain field. So let's take a look on the right side. We are looking at this AR. AR is basically the aspect ratio of a wound which we have come up with. We wanted to look at that if you have a very long wound versus a short wound, how would they, what kind of strain fields do you see due to that, right? So let's take a look. So this is how a DIC setup or a final set of results look like, right? So you are looking at these different stages. So frame 1 on the very top left, t is equal to 2 seconds. So while you're doing the test and you're taking the video, this is a t is equal to 2 seconds. Then you have a t is equal to 24 seconds. This is the frame 8 based on how I've broken down the entire video into, let's say, 30 or 40 frames, right? Then at t equal to 57 seconds, which is my frame 12 in this case, I see the specimen has elongated quite a bit. So we are looking at this particular wound shape, which is an elliptical wound, and what we see is with the colors, the strains. These are Lagrangian strains, sometimes known as, but you can compare them with von Mises stress, right? So one of the majority part of this upcoming sessions would be an introduction to finite element modeling of soft tissues, right? There we are going to get all this colored maps of strain localization, how the strain is distributed, how the stress is distributed, these kind of things we are going to learn, right? So the digital image correlation allows us to compare the experimental results with the computational results like what you get from finite element modeling and validate the finite element model, right? So that's why this DIC technique is very often used in the industry as a validation tool. Also, it is a good tool to understand the local mechanics of the soft tissue. So overall is okay, like overall property due to a wound is something, but what is happening at the local level, what is happening at the periphery of the wound, right? So what we can see very clearly is in frame 1 we have some red zones around the wound, right? As we go to frame number 8, this red zone has now been localized on the left side, right? That means you have a very high strain zone followed by all the very low strain zones, which are the purple and the blue, right? Whenever you have this kind of a condition, that zone or that local point is highly susceptible to a fracture or a rupture. So please remember, as a rule of thumb, whenever you have a very high strain zone surrounded by a low strain distribution, that means that is a place from which a fracture can initiate. This is a point of concern. And finally, what you do see in frame 12 is the strain localization is still where it should be, and finally that place encounters a fracture from that location. There is some curling in the specimen, and that is where the specimen is going to break when you push it or pull it even more, right? So this is very valuable information, and this is unique to every wound shape. If I change this to a long wound, it is going to give a very different story here, like in terms of local loading, right? This is very important to know, because this is how you know the wound is going to behave in the different cycles of healing. So whenever you get a wound on your body, typically what happens is uh, that particular portion of the skin is missing, right? So there is a lot of fibroblast and other things like biochemical operations which happens to create a healing, but you will see commonly a stretched skin on the side, because you have a different material at the portion of the wound, and you have a very stretched skin on the side which is not able to apply all the natural tensions properly, which is usually all balanced when you don't have a wound, right? So you see a very stretched skin, that is the biaxial loading of the skin. Or so these kind of loadings can cause the wound to not heal properly sometimes, if you are not selecting the right kind of stitching or right kind of healing operation, right? So that's why understanding what is happening at the local level for different wound shapes is of utmost importance. Another application of this is when a surgeon is going to do some operation, let's say open heart surgery or trying to operate on the stomach, he has to cut certain portions or make certain incisions to reach to an organ. What is the correct type of cut or incision which is there? Is it an oval cut, or is it a circular cut, or is it a straight cut? What kind of cut is ideal? By ideal, I mean what cut is going to heal after the operation very quickly. So these kind of information can only be learned if you look at the local mechanics of the soft tissue. So these wounds can be compared with the cuts. It's very similar to the cuts, right? So on the right side, what you're seeing is we are doing a very close particle tracking at 4 different points in the wound. We have zoomed into the wound and we are tracking the different strains which are generated at these 4 different points. And what we do see is the point on the very left, which is P1, is showing the maximum amount of strain buildup, and we clearly get the value in the time frame what the value of the strain is. And this also reiterates that that is the point of the highest localized strain development, and that is the possible point of rupture, right? Okay, so let's talk about the next application of soft tissue simulants, which is for the testing of artificial skin grafts using simulants, right? So let's take a very quick snapshot of what skin grafting is. So skin grafting is a technique which is applied when somebody has experienced a very severe kind of burn injury or injury which has led to removal or damage to a lot of skin, right? So whenever a lot of skin is damaged on the body, then the body cannot heal itself, or normal suturing is not good enough. So you need to place a skin graft, which is nothing but you take a healthy piece of skin from another location of the same human body, typically from the thigh region. So you take this healthy piece of skin, you create a pattern with this is known as a slit pattern, using a device which is known as a skin graft meshing device. And using this pattern, this allows the skin to expand to a certain version. So just the normal skin is not going to expand. So you take a small piece of skin, create this pattern, and now you can expand the skin and place it on the place of injury and then suture it, and this will allow the skin to heal much more quickly, right? So this is usually the technique of grafting. So in very severe injuries where somebody has lost has a 30% burn or 40% burn or something more, you cannot be extracting so much skin out of the human thigh. That will cause the person to suffer even more, right? Sometimes you take skin from like other cadavers and other places, but that's not very successful. So typically it's an autograft, like from where you take skin from the same body. But the primary concern here is skin is very expensive in the area of burns. So can you take a very small piece of skin and place a very unique pattern rather than a normal slitting pattern, which can allow the skin to expand beyond its limit 4 or 5 times, so that you can cover a very large area. So that is the research problem which we are trying to solve through this research. So let us dig in more. So the expansion of the skin grafts play a key role in treating severe burn injuries, like I mentioned. In this work, the expansion potential of skin grafts, expansion potential is how much they can expand. Skin grafts with a novel rotating triangle shaped auxetic incision patterns were investigated. What is an auxetic? Auxetic is a very unique type of material configuration. It is sometimes known as metamaterial. If you just look up metamaterial, you will see what auxetics are. So like any soft tissue, when you pull a sample of soft tissue, it contracts in the middle. In auxetics, you have the same soft tissue with certain patterns. When you pull it, it will not contract but it will expand. This is the theory of auxetics. It is known as negative Poisson's ratio material or an expanding material. And this expansion is just by the virtue of the pattern which is within that material, right? So one of the common patterns here is known as the rotating triangle pattern. These have been carefully curated through a lot of research which is ongoing in the world of auxetic metamaterials, right? So we had picked this rotating triangle shape. So a skin simulant was developed to try and test this new unique kind of patterning, which we cannot do in a cadaver skin that easily because it's scanty and has a lot of ethical clearance issues. Here we can do it like without any ethical clearance, right? And you don't want to do it on a live human tissue because this has not been proven. We just want to test it like using a different pattern and see whether the expansion is larger than what is there in the industry, right? So the skin simulant was employed in a range of rotating triangle configurations with internal angles varying from 0 to 135. These are different pattern configurations, right? Were tested through the development of skin graft simulants. So when we created grafts using the skin simulant, we are calling them as skin graft simulants. So that has just the patterns within the skin simulants, right? So mechanical testing on a UTM and digital image correlation both were used to characterize the Poisson's effect, or how much is the expansion rather than contraction, right? Or what is the overall Poisson's effect. The meshing ratios, how much has the skin expanded. So meshing ratio is nothing but the uh, expanded volume divided by the initial volume of any material, right? And the induced stresses of the skin graft simulants. While we are expanding the skin, we do not want to go beyond the ultimate tensile strength of skin at any point, because that may cause the skin to break, right? So there are a lot of parameters we need to be careful. We cannot be expanding skin to infinity. We can expand it to a certain limit. Beyond that, the ultimate tensile stress point may be reached and the skin may break from certain points. We cannot be stretching it beyond limits, right? So such experimental findings on expansion potentials and estimations of mechanical properties with auxetic skin graft simulants have not been studied or reported to date and would be indispensable for further research in skin graft expansion. So without the skin graft simulants or the skin simulants, we can never do this research, right? So here is a schematic of the skin grafting on the right side, and I've explained how the skin looks like. And grafting is basically, like I had mentioned, you take a small piece of skin and basically expand it through meshing and place it on the burn region, right? Let's go further. So these are the different designs of auxetic rotating triangle shapes which we developed. The first picture in any design, you're looking at the unit cell, which is the primary unit of this, and on the second and the third picture you're looking at the overall sample where all these unit cells patterns are distributed, right? So the rotating triangle is nothing but it's a triangle which kind of opens up, right? At 0 degree it is completely like a Y shaped pattern. At 135 degrees it's almost like a hexagon, right? So this is how the pattern is, like this is the geometrical modeling of the auxetic patterns. So next what we did was we created molds for this patterns through reverse designing on CAD modeling, and these molds were used to cast the skin simulant material to develop skin graft simulants. So what you're looking on the right side are the skin graft simulants, left side are the 3D printed molds, right? So 3D printing has been immensely beneficial for us. So all the skin graft simulants are now clearly marked 0 to 135. The geometrical auxetic models were used to develop the negative graft molds, and 3D printers, like I said, were used to develop the final skin simulant material. Skin simulant material we had already explained, we have the composition for that, right? So this is what we used for further testing. So now we have put a spray on this, all these test specimens as well, like it's a little black spray because that was giving the right contrast with the background, which was skin color. You can see the UTM configuration where all the samples have been developed in a way that a lot of the samples are not eaten away by the clamp ends, right? That's why we have that extra edge, extra edge. So now they are all clamped and tested under tension, right? All these different samples. So while we do this, we are also recording a video using the camera, and we'll be post processing the data to look at the local strengths, what I've just explained with DIC. So this is what we find out, very interesting results. From a Poisson's ratio standpoint, Poisson's ratio typically is from 0 to 0.5 from normal materials, but here the Poisson's effect is very unique. So we are looking at an overall Poisson's ratio which is changing as you go from 0° rotating triangle shape configuration to a 135°. From negative 0.9, negative Poisson's ratio means this is expanding, positive Poisson's ratio means it is contracting, right, during a uniaxial tension test. So we see a negative Poisson's ratio which is slowly getting converted to a positive Poisson's ratio when you are using a different configuration. So this clearly says that the Poisson's effect is the maximum in the 0° configuration, because this is a lot of chance of opening up, right, which is intuitive. We also compared the engineering stress, how much stress is developed in each of these samples, overall stress, that is through a UTM test, right. So we have plotted the engineering stress versus engineering strain. We've also looked at the digital image correlation results on the right side, where we are looking at the imaging based results, and we are seeing places where you see a lot of holes or voids within the final stretch specimen when you try to expand it. These voids are not desirable, right. If you have a lot of void between the burnt skin, it is not going to, the cells are not going to proliferate and the skin is not going to heal that quickly. So ideally what you need is, you need a configuration or a skin graft in future which has a configuration or a like a shape of pattern which is very unique, in a sense that it is not giving rise to a lot of stresses so that the skin may break. That is not ideal. It should not create a lot of voids, right. It should create a lot of expansion. So there are three important parameter outputs which we have to be careful about, like while designing artificial skin graft simulants, right. So with that, we also looked at the meshing ratio, which is the expansion ratio. From 0° to 135°, it has been closely decreasing. So now we can very clearly pick that 0° is the most appropriate this one appropriate configuration, for which this will allow you a lot of expansion possibilities with a low stress development and a limited void setup. So these we ran a battery of tests, we did a lot of research, this is well published, you can look it up, and this is where a lot of these techniques were developed. Okay, so the next example of the soft tissue testing or using soft tissue simulants is of testing of a hernial mesh. What is a hernial mesh? Hernial mesh is a mesh which is mesh material which is used for repair of a hernia. Hernia is nothing but when you have an organ trying to protrude out of a soft spot in the skin or soft spot in the muscle, and then it finally comes out. It's an extremely painful process, typically happens around the abdominal region. Majority of us would know what hernia is, right. So an organ is trying to come out of basically the fat part, and so typically how this is operated is, you want to put this organ back surgically into where it came from and put a surgical mesh which is usually built up of a polypropylene or a plastic semi-plastic or polymeric material, and that mesh usually forms a hammock which doesn't allow this organ to come back, and you stitch this mesh on the side as if like you've just blocked a hole, right. So this is how hernia repair surgeries are conducted, but you have close to this number is huge. We are looking at 2 crore hernia repair surgeries per year. This is from literature. Hernia surgeries with prosthetic meshes have a lot of recalls and have a lot of issues. Some of the common issues which are reported across or around the globe are pain and infection, which is a biological issue that you cannot correct through study of any mechanics, hernia reoccurrence, mesh contraction, and mesh failure. These are the three different areas which we have identified about the hernia mesh issue, which can have an effect due to the loading, the incorrect amount of loading which is getting applied on the mesh, that is probably causing the meshes to fail. So we wanted to study this more. So majority of the literature studies so far have focused on mesh biocompatibility, which is basically to look at whether the mesh is compatible within the body, and that has been done through animal models, and dry and wet mechanical test, where a mesh has just been pulled in different directions, and through uniaxial and biaxial loading this has been understood that how the mesh behaves. But this is not exactly what is going on inside the human body. You have the mesh typically sutured with a soft tissue, and you want to study the interaction between the mesh and the soft tissue. So the literature gap here is lack of mesh and human tissue interaction tests, and one of the reason this is not there is lack of human tissues itself. You cannot be taking an abdominal tissue that quickly and running these tests, right? So we decided to come up with a soft tissue simulant which simulates the pelvic tissue or the abdominal tissue, and we created, we took a real mesh from, this is from Proline mesh from Ethicon, and we from Johnson and Johnson, and basically we took this mesh and we basically sutured this mesh along with uh, the soft tissue simulant, how it is originally sutured in a real suturing scenario or a surgical scenario, and we ran some overall tests to look at the overall property in a UTM. We also developed a finite element model to study the same what is happening at the local region, right? We studied this at different strain rates also, because these different kinds of movements are experienced during different gait cycles, right? So we did all these experiments, and some of the very interesting results which we found out is, for stretch or strain less than 0.5, the tissue is the major load bearing component. However, when the strain increases, overall strain increases over 0.5, the prosthetic mesh underwent permanent deformation. So after a certain strain, the prosthetic mesh was going through some deformation, and there was minimal effect of strain rates, indicating that the prosthetic mesh was a dominant load bearing component. So the figure on the right is just showing some of the results where we are looking at just the prosthetic mesh stress strain profile, just the pelvic tissue surrogate or the simulant test stress strain profile, and the overall sutured composite model stress strain profile. So sutured model is lying in between the prosthetic mesh and the tissue surrogate. Tissue is softer, mesh is stiffer, and the overall property is between that. So other things which we did find out, and very interesting result, we found out that there is a lot of stress concentration on the prosthetic mesh strands when we zoom in. This is through computational modeling, where due to the unit cell, how the mesh is looking like from a pattern standpoint, that is very unique. So this was a very key finding. So the pattern of the mesh has a very unique implication on how the mesh could possibly fail. So this is a very important clinical information which a doctor would not know. So this is reported in one of the publication when we where we did this extensive research both experimentally and computationally, and finally found out that the culprit here is the mesh design. So if we can control the mesh design properly and have the right unit cells, then the stresses could be less and the meshes could possibly fail less. This is an ongoing research, so we are going to conduct tests on different mesh designs, right? So this is these were a set of examples which I wanted to just take to just showcase that what is the importance of overall soft tissue simulants and how this is widely applicable in different research scenarios, right? So with that, I would like to conclude this session, and stay tuned for more exciting lectures upcoming in this course, right? Thank you.